All right, folks, and welcome back. In this video, we'll be looking at the reciprocal function. So the reciprocal function in complex analysis looks like this, right? F of z is equal to 1 divided by z. Okay. We'll look at where rational functions are undefined very soon. And the zeros in the complex plane is pretty crazy. So for now, let's look at this function. So this here is what's called the reciprocal function. Okay. And in particular, the complex rational function. Okay, the complex rational function in general would be a form f of z equals to p of z divided by q of z, where p of z is equal to a complex polynomial. Oh, this should be z. Okay. Complex polynomials. P and then Q, right? So in terms of polar coordinates, it's going to help. So in terms of polar coordinates, this function is going to help us out a little bit, right? So given that z is not 0, okay, the w coordinate in the w plane would correspond to 1 over r times e to the minus I theta. Okay, this is in terms of polar coordinates. So what's happening is 1 over r will be scaled depending on if r is greater than 0, r is less than 0. And then e to the minus I theta, you're rotating, you are reflecting angles about the real axis in this case, right? So let's see how this function is interpreted in much greater detail. So first let's look at the inversion of the unit circle, right? Modulus of z equals to 1. And this will comprise of two functions. So this we'll look at first, 1 over r times e to the I theta. Okay, e to the I theta over r. This is just the inversion of the unit circle. And what happens is if I take points on the, so this is the z plane, right? And if I take a point on that circle, let's say z1, right? And if I take another point, z2 in the unit circle, inside the circle, and if I pick another point, z3, that's outside, let's say it's over here. Okay, so z1, this is on the circle, so the radius is 1. So in terms of polar coordinates, this would so the modulus of z1 is 1, and then so if I write out e to the I times theta 1 as its polar coordinate, G of Z1, well, this will let's see. This will stay the same, okay? Because as you can see, the theta in our function is it will be the same as the theta in Z, okay? So in the W plane, so if I look at the circle of radius 1, let me write it down here. So this circle represents a circle of radius 1. G of Z1 will be stationary, right? So G of Z1 will be this point, e to the I theta 1, right? It's pretty straightforward. Now, if you look at the point Z2, the modulus of Z2 would be some point R2, but that is less than 1. It's inside the unit circle, right? So it's inside the unit circle. So um, so what is also going to happen is so the theta is kept the same. So under G of Z2, what's happening here is it will be 1 over R2 e to the I, let's say theta 2, right? So if okay, so this is theta 2 here, right? So G of theta 2, G of Z2, excuse me, will be a point that is outside of the unit circle, G of Z2, right? This should be R2. Since R2 is less than 1, right, 1 divided by R2 is going to be greater than 1, right? It's going to be greater than 1. All right. So, all right, so you'll have points that are outside of the unit circle, okay? Z3 is a point that's outside of the unit circle, so we'll have a radius R3 that's bigger than 1, okay? So under G of Z3, if we're going to assume that the radius is, I'm sorry, the angle is the same, we'll have 1 over R3 times e to the I theta sub 3, okay? So in this case, Z3 would be a point that's inside the unit circle. So G of Z3 is here. So if I zoom in just a little bit more and write this clearly, G of Z3 would be a point that's inside the unit circle. So this function, G of Z, this will invert points with respect to the unit circle. Okay? And it's just depending on what how big the radius is for different points on the complex plane. Okay. There's also going to be the complex conjugate. The complex conjugate function. Okay, so they label this as C of Z equals Z bar, right? So essentially what happens here is for any complex number, Z, right? So C of Z, well, it just makes the imaginary component negative. So Z bar would be a point that has the same magnitude, the same radius, but if I just align this properly, it just reflects about the real axis, right? So if this is the real axis and the imaginary axis. So it takes points and it reflects them off the real axis, right, geometrically. Okay, so so this would be theta, and this angle right here, this would be minus theta, right? So geometrically speaking. So algebraically, in terms of polar coordinates, z, in terms of polar coordinates, this would equal to r times e to the I theta, right? And by properties of a complex conjugate, you can multiply by the complex conjugates of each of the numbers. It's like this. R is a real number, so that means the R conjugate equals to R. So this is R times e to the I theta conjugate, right? Now, e to the I theta, well, this equals to cosine theta plus I times sine theta, right? So therefore, e to the I theta conjugate, this equals to cosine theta minus I times sine theta, right? Now, in trigonometry, we can replace theta with minus theta, right? And this is plus I times sine of minus theta here as well, okay? So this would equal to e to the minus I theta. So therefore, we can say that e to the I theta conjugate, this is equivalent to saying e to the minus I theta, okay? So thus, c times z in terms of polar coordinates, z bar, implies that z bar is equal to r times e to the minus I theta. Okay? E to the minus I theta. So, what does this mean? The reciprocal map. So what this means is that the reciprocal map, I'll say W, 1 over Z, is equal to a composition of complex functions, C of G of Z, right? Okay. C of Z was Z bar, right? And then G of Z was the inversion function, right? E to the I theta over R, right? And in terms of polar coordinates is R e to the minus I theta. Okay. So so what we do here is we invert functions in terms of the unit circle first, and then we reflect points about the real axis. So that's the whole summary of plotting points of the complex plane under this reciprocal function. So let me write out the image, how to find the image of a point z naught in the complex plane under this this reciprocal function. Okay, so this is how we do it. First we want to invert z0, z naught in the unit circle. And then 2, we want to reflect the result in step 1 across the real axis, right? Okay, so that's basically it, right? So for example, right, so if I have this example, find the image of the given set under the map W equals 1 over Z. Okay. And then suppose we have the following set. So this is the circle of radius 5. Okay. So I want you to pause the video and look at what this image of the set would look like. Okay, so this shouldn't take that much time to think about. So if we have the set S, which is the circle of radius 5 in the Z plane, right? The set S prime, right? S prime. Well, just look at what W is in terms of polar coordinates, right? Since we have a circle or some other type of circular region in the Z plane, you want to use polar coordinates, right? So, so W equals to 1 over R e to the minus I theta, right? So we invert points with respect to the unit circle. So here's the unit circle here in the S plane. So what is going to happen is we're going to have points which look like this. So if we invert points so if we reflect points about the real axis, well, we're just going to get the same circle in the W plane, right? So this point will be here, right? And then this point will be here. And if we reflect all the points on the circle radius 5, well, we're just going to get the entire circle of radius 1/5 in the W plane. So, so this is the unit circle. Again, let me do the same color. So this is the unit circle right here. The image S prime would be a circle of radius 1/5, right? Okay. And we'll just get the whole circle of radius 1/5. All right. So hopefully that made sense. How about this example? Now this is going to be interesting, this one. We want to find the image of the reciprocal function for the line y equals 4. Okay. So we have W equals 1 over Z. So this is the Z plane. And then we're going to look at the line y equals 4. Right? Y equals 4. Okay. So we want to look at what the image looks like in the W plane. So pause the video. I want you to think about this and try to come up with a solution. Okay. All right. I assume you worked on this. So let's look at how we would approach this. So, okay, let me do a divider here. So we know that the reciprocal function, 1 over Z, and the thing we want to do here is we have a value for y that's constant, right? So in this set, Z would equal to, well, x is varied plus 4i. So a complex number would look like this. So the best way to go about this is look at the real and imaginary components of the reciprocal function, right? In terms of x and y. So if z is equal to x plus iy, then w would be 1 over x plus iy, right? But we need to, so this is division of complex numbers here. So what we need to do is multiply the numerator and the denominator by the complex conjugate of the denominator, right? So this equals to x minus iy divided by, we'll have x squared plus y squared, okay? And so w is equal to the real component, y squared, plus the imaginary component, which I'm going to write like this, minus y divided by x squared plus y squared. Okay, so u, the real component, is x divided by x squared plus y squared. And then v is equal to minus y divided by x squared plus y squared, right? Okay. So under complex numbers of this form, x plus 4i, right? Y coordinate is 4. So the u, the real component, is x divided by x squared plus 16. And then the v component is minus 4 divided by x squared plus 16. Okay. So label this as 1 and then 2, right? From 2, what this means is we'll have v times x squared plus 16 equals minus 4, which concludes that x squared plus 16 equals to minus 4 over v, right? Minus 4 over v. So what that means is from equation 1, what we can say is that u is equal to x divided by minus 4 over v, right? And so what that means is x is equal to minus 4u over v. Okay, that's good. All right. So that's a good thing. So therefore, if we substitute that value back in the second equation, we'll get here is v is equal to minus 4 divided by minus 4u over v squared plus 16, right? Okay. So we'll have v times minus 4u over v squared plus 16 equals to minus 4. And if we simplify all of this, we'll have 16u squared over v. So we'll have, so this quantity is minus 16u squared over v squared times v. We'll have 16u squared over v plus 16 times v equals to minus 4. If I multiply both sides by v, right, I'll have that 16u squared plus 16v squared equals to minus 4v. Okay. And so we'll have 16u squared plus 16v squared plus 4v is 0. And if I divide both sides by 16 altogether, I will have u squared plus v squared plus 1/4 v equals 0. Okay. So from here, what we're going to do is we're going to initialize the complete the square method. Complete the square method on v. So we'll have u squared plus v squared plus 1/4 v plus blank equals 0 plus blank. All right. So to complete the square, we look at the coefficient on v. So in this case, it's 1/4. We divide it by 2. So that is equal to 1/8. Next, we squared that number, which is 1/64th, and they will go into these blank spaces here. So this will be 1/64th here, and then 1/64th here. Okay. So the V quantity would be a perfect square. So we'll have U squared plus V plus 1/8 squared equals to 1/64th. Okay. So this here is a circle. The circle in the W plane, right? So this will constitute a circle. The radius is 1/8, and the center is at, so in the UV plane, it's 0 and minus 1/8. Okay. 0 and negative 1/8. So in terms of W, so if we let W equals to U plus IV, then if we square root both sides, we'll have U squared plus V plus 1/8 squared equals to 1/8. So in terms of the distance, right? So we'll have W minus 1/8 I equals to 1/8. So this is the image of the reciprocal function in the W plane, right? As you notice, we solved for X. Where was it? Right here. This will constitute that V can't be 0, right? So in the W plane, so this can't be 0, but nevertheless, we'll have a circle of radius of 1/8. 1/8 I. Let's see. I'm sorry, this is plus because this was plus here. So, yeah. Okay, so, yeah, so it'll be below the real axis in the UV plane. Okay, so this is our W plane, and that would be the image. Okay, and this is important to point out. So, uh, so, so this is an important fact of mapping lines to circles under the reciprocal function. Okay, so so the line x equals k, where k is not 0, k is not 0, maps onto the circle w minus 1 over 2k equals to the modulus of 1 over 2k, right? And then the second fact is the line y equals k. If k is not 0, maps onto the circle w minus 1 over 2k times I equals to the modulus of 1 over 2k, right? And this works out too, because what we looked at here was the circle here of radius of 1/8 centered at 0, negative 1/8. Okay. Let me label out the center here. So, and it really fits out with this fact that's labeled out here. So, so yeah, that's important to point out. So let's do one more example. Let's see. So if I have this set, so line y equals x, and I'll emphasize this set here. So this is a slice of a circle of radius 1/2, right? So try and pause the video and try to look at how to figure out the image of the set under the reciprocal function. Okay, so hopefully you work this out. And the thing to look out for here is that this slice of the circle of radius 1/2, it's constricted in between two lines, right? So in the z plane, so this slice is within the real axis, so y equals 0, and then in between the line y equals x, right? And so therefore, the argument of this slice, well, it's in between minus pi and well, pi and 5 pi over 4, right? Minus pi and minus 3 pi over 4, right? Or pi or 5 pi over 4. Okay, so yeah, minus 3 pi over 4. Okay, so all right. So if we look at points on the real axis, x equals 0, just to point out, the function in terms of the real and imaginary components was x squared over x squared plus y squared and plus I times minus y over x squared plus y squared. Okay. So if the x is 0, what we will have here for points in W, well, this would be equal to 0, 0 minus 1 over y times I, right? So therefore, in the W plane, this will correspond to points on the real axis in the W plane, right? So so I'll label out the real axis in so u equals 0. Okay. All right. So likewise at the points where y equals x, well, the points in the W plane, so that will be so this is x squared over, well, x squared plus x squared, and then plus I times minus x over x squared plus x squared, since y is x, right? So we'll have x squared over 2x squared. Oh, shoot, that's x. It's excuse me, so that's x here. X over x squared plus x squared, so that is 1 over 2 times x. And then minus 1 over 2x times I. Okay, so we know that x can't be 0. So what we will have here is u is equal to 1 over 2x, and then v is equal to minus 1 over 2x. So we will have the line v equals minus u. So v equals minus u. So we'll have this line here, right, in the uv in the w plane. So v equals minus u would be this line here. And along the slice where the circle is of radius 1/2, right? So if I look at the slice of the circle where the radius is 1/2, well, the r is 1/2, and the argument is in between minus pi and minus 3 pi over 4, right? And so what we do is we reflect, so we invert points with respect to the unit circle. So in the W plane, we will have a circle of radius 2. Okay, so we'll have the circle of radius 2. And then we're going to have points in the second quadrant. So we reflect points on the real axis in W. So this would be the corresponding set in S prime. So so it would be 3 pi over 4 to pi. Okay. All right. So this would be the set S prime here. Okay. So hopefully that made sense. So let's, and I want you to work out these problems to check comprehension. As always, just let me know in the comments if you have questions. So page 97 through 98. Also, I included a link of the free textbook in the description of this playlist, of the complex analysis playlist. 2, 4, 6, 10, 11, 15, and 18. Okay. Hopefully you enjoyed this. If you have questions, always, again, just let me know in the comments. I'll see you all in the next video. Good luck.